Hi, it's Mr. Anderson, and in this podcast I'm going to hopefully show you how to solve Hardy-Weinberg problems. Here's Hardy, here's Weinberg. They came up with this wonderful idea of Hardy-Weinberg equilibrium. It's used by geneticists and evolutionary biologists, but little did they know they would plague biology students forever as they try to solve these problems. And so this would be a typical Hardy-Weinberg problem. We've got 16% of the population unable to taste a chemical, and they're asking a number of questions like how many people are heterozygous, what's the allele frequencies. And when I have students who struggle with this, basically all these terms are kind of swimming around in their head and they have no idea what's what or where to even start. And so I want to kind of go back to basics and show you what a gene pool is, and then show you how to solve some of these problems. And so let's start with a sample population. Let's make this population really, really small. Let's say we have 10 people. So we've got 10 people here, and half of them had red hair. And so to have red hair, you have to have two red alleles. So this would be a person with red hair, red hair, red hair, red hair, red hair. So half of the people have red hair, and then half the people don't. And so this would be somebody who maybe has black hair, or this could be somebody who has blonde hair, or it doesn't matter, but they don't have red hair. And since it is a recessive, you have to have two copies of it. Okay, so this would be the population, and this would be their phenotypes, physically what they look like. But if I take all those genes in a population and scramble them up and put them in a pool, then it becomes a gene pool. Now they're not associated with one individual anymore. And so basically, this is a gene pool. And so there are two values that I want to throw out. The first one is P, and the second one is Q. P is going to be the allele frequency of the dominant trait. Okay, so what's the dominant trait? That's going to be this non-red. And so I'm going to say 1, 2, 3, 4, 5, 6. There's 6 of them. And there are 20 total alleles here. There are 20 total genes. And so our P value would be 0.3. And so now how do we figure out the Q value? Well, the Q value, I could count up all the red ones. It's going to be 14. And then I divide that by 20, and it's going to be 0.7. Another quick way to do that is if you figure out that this is 0.3, P plus Q will always equal 1. And so I could have just taken 1 minus 0.3, and that would have given me my Q value. And so what does this mean? Well, in a gene pool, this means that 30% or 0.3, be cautious of percents because they can get you in trouble when you're solving the problems, but 30% of the individuals are going to be, of the genes, are going to be of the dominant, and 70% are going to be of the recessive. Now, if you know anything about genetics, we can figure out where the rest of the Hardy-Weinberg comes from. So what are the odds if I were to just grab one of these, if I were to just randomly grab one of these genes out of the gene pool, what is the odds that that is going to be recessive? In other words, what are the odds that it's going to be red? Well, the odds would be 7 out of 10. What are the odds if I pull 2 of them out that they're going to be red? Well, knowing anything about the law of multiplication, that's going to be 7 out of 10 times 7 out of 10. And so that's going to be 49 out of 10, or that's going to be 0.49. So grabbing 2 of the reds, it's going to be 0.49. Let's do that again with the blues. What are the odds of me pulling a blue out and then another blue out? It's going to be 3 out of 10 times 3 out of 10. And that's going to be 9 out of 100. And that's going to be 0.09. Okay, so for me to get 2 of the recessive, it was 0.49. For me to get 2 of the dominant, it's going to be 0.09. So what are the odds of me pulling out a blue and then a red? Well, to do that, it would be a 7 out of 10 of the red times a 3 out of 10 of the blue. So that's going to be 21 out of 10. Out of 100. But I don't have to necessarily pull out a red on the first time and then a blue on the second. I also could do it by getting a blue on the first time, 3 out of 10, times 7 out of 10. And so that would be a 21 out of 10 as well, out of 100. And so I have to add these two because I could get a red and a blue one in 2 ways. And so when we look at the equation for Hardy-Weinberg equilibrium, let's go to that. Where do we get this p squared, 2pq, q squared? P squared is basically taking the allele frequency of the dominant. When we were solving this problem, that was 0.3, and then we simply square it. And that's going to tell me how many individuals are homozygous dominant. In other words, they have one of each of the genes. What are the odds of me doing this one? In this case, our recessive value is 0.7 squared, so that's going to be 0.49. That's the homozygous recessive individuals. And then the heterozygous individuals are going to be 2 times P times Q, because you could get it either red-blue or blue-red, so either of those. And so this is where this term comes from. And so basically, even though I may have lost you at this point, the big thing to remember is that if they talk about the allele frequency, then they're talking about the p-value and the q-value. If they're talking about individual people or individual organisms or individual phenotypes, then they're talking about p squared, 2pq, and q squared. Because it's vital when you're trying to tackle one of these problems that you know what you're given on day one or on the first step. And so let's try this problem again. So what does it say? It says, let's break down this thing. 16% of a population is unable to taste this chemical. These non-tasters are recessive for the tasting gene. So if you think you know how to do this, you may want to pause the video, try to work it out, and then I'll show you how I would work it. Pause video. Okay, so here we go. So basically, what are they telling me? They're saying 16% of a population. So are they talking about genes or are they talking about people? Well, they're talking about in a population. They're saying 16% of the people are unable to taste it. And so what are they telling me? They're telling me, you know, p squared, 2pq, or q squared. Almost always when you're solving one of these problems, they have to tell you the individuals who are homozygous recessive. And the reason why is if you're dominant for the trait, we can't tell if you're homozygous or heterozygous. So they almost always start with q squared. So they're telling me q squared equals, and now we want to get rid of the percents, we're going to say equals 0.16. Okay, so 16% or 0.16. So now my goal in any problem, even though I haven't even looked at the questions here and what they are, is to get to P and Q. Because if I can get to P and Q, I can solve any problem. Okay, so how do I get to Q? I could take the square root of this side, I could take the square root of that side, I could say Q equals 0.4, I could say P equals 0.6, and now I can just smile to myself because I know I can solve any problem that they ask me with just a little bit of common sense. So I got my P and the Q value. So let's look at what questions they ask. Number one, what percent of individuals in the population are tasters? Well, let's use a little common sense. They're saying that 16% are non-tasters, and so that means that everybody else has to be a taster. So I would say 84% on this first one. Okay, let's look at the next question. What is the frequency of the dominant allele and what's the frequency of the recessive allele? Well, the frequency of the dominant allele, we've already solved that. That's going to be our p-value, so that would be 0.6. And then what about the recessive allele? That's going to be 0.4. That's going to be my q value. So I'm golden so far. Now let's go to the next one. What percent of the population are heterozygous for the trait? So now we have P and Q. We can solve for this. Heterozygous, remember, are always going to be those individuals that are 2pq. So it would simply be 2 times P, which is 0.6, times Q, which is 0.4. So this is going to be 0.24. So I would say the total is going to be 0.48. Or if we're looking for a percentage here, I would say it's 48%. Okay, so the majority of questions you get when you're solving Hardy-Weinberg questions, they're almost always going to start by telling you the individuals who are q squared. And so if you remember that and it's an individual, then you're going to do well. Let's go to another problem though, because this is another way you can be asked this question. Let's look at this one. This one, the delta 32 mutation, a recessive gene, gives humans protection from HIV. The allele frequency in a town in Sweden is 20%. Okay, so what are they telling me here? This is another thing that they can tell you. They could tell you the allele frequency, so this is super important. They're telling me the allele frequency, and they're also saying that that's recessive. Okay, so what have they told me? I know right away that they've told me Q. In this case, they're telling me that Q equals 0.20. I say P equals 0.8. And we know that immediately right away. And so now I, again, smile to myself because I can solve any problem they ask me. Okay, so let's look at this one. What percent of the population have 2 copies of the gene and are therefore immune to HIV? So now they're saying 2 copies of this recessive gene. So what are they telling me? Now they're saying solve for Q squared. So Q squared equals 0.2 squared. And so Q squared equals 0.04. Now, a common mistake that people make when they're solving this is they take 0.2, they square it, and in their head they somehow think that's going to be 0.4. And why is it not 0.4? Well, if you have that mistake, trust me, put it in your calculator, I'm right. If we take 0.2 squared, a good way to check that is to write 2 over 10 times 2 over 10, and that equals 4 over 100. And so that equals 0.04. Okay, so we've solved this one. It's going to be 0.04. Let me clear that out. Next one, they're saying what percent of the population are less susceptible to the disease since they're heterozygous? Oh, so to solve that one, again, this is going to be 2 times P times Q. So that's going to be 2 times 0.8 times 0.2. And so I get like 0.32. Or if they're asking what percent, I would call that 32%. Okay. And so that's how you solve Hardy-Weinberg problems. Remember, pay attention because they're going to tell you specifically either a q-squared value or give you a way to figure out q-squared value, or they're going to start by telling you allele frequency. And you want to work to P and Q, and then you can solve anything else. And so I hope that's helpful.